Usually you want to first hear the lecture and then you applaud. But the applause is for the summer school. Okay, cool. And thanks to the organizer again for all they've done. So, guys, let's start with the last lecture. Maybe like a super lightning summary of what we've done up to now. In all the discussion about elasticity, essentially we've been considering equation of motions. For the dynamics of a field, for example, the displacement field, assumed over damped, hence one derivative. And then the crucial thing is that the right-hand side of this equation of motion was expressed as a divergence of a stress tensor. And this stress tensor was given by a linear relationship with respect to the strain. Okay? This is UKL is dk, let's say dkul. So naturally, two derivatives came, and you had the structure of a diffusion equation. The crucial aspect of this equation is that it's linear. It's linear in U. The reason why we were so interested in it is that this right-hand side, whenever KIJKL, sorry, this is not a U, it's an L. Whenever this object contains an odd part, the right-hand side cannot be expressed as a variation of a potential. Okay? And so this is an example of dynamics that does not follow an optimization principle. Okay? So what I'd like to do today, I would like to follow on that and study phase transitions that cannot be expressed or cannot be understood as, for the most part, as variation of a potential, not certainly an energy, a potential that is an energy function. And so let's try to recap a little bit how we think about phase transition normally. Let's start with something that you're all familiar with, which is the Ising model. Okay? So in an Ising model, you may have a situation in which you have a bunch of spins that I'm going to denote as I and J. Actually, let me switch to Latin, to letters, because in this case, I'm not going to talk in this specific equation. I'm not going to be talking about A and B being a component, Cartesian component, but rather labels for the indices of the spins that you can imagine distributed on a lattice. So in the Ising model, there's what people call an exchange interaction, JAB. Typically, this is taken to be a constant that is greater than 0 if what you want to do is to promote alignment of the spins. And when you solve an Ising model, the story is always to study a finite temperature with a given amount of noise, the competition noise that tends to disorder a media, and hence favor configuration where there's an equal amount of spin up and spin downs, versus an ordered configuration in which all the spins are pointing either up or down. So the competition is between an ordered static configuration and a disordered one. Okay? Now, please notice that, of course, this JAB need not to be equal to a constant. Okay? Could be dependent on the spins involved. But what I would like to draw your attention is, imagine what happens, and following that, usually the dynamics that one imposes on the system is that the dynamics of the spin will be given by a variation of this energy with respect to the degrees of freedom. Okay? So you tend to go downhill, maybe with a minus. Okay? Now, what I would like to draw your attention, and of course, I mean, once you do that, if you add a quadratic form for the spin, then this derivative would be linear. Okay? In fact, it would be sum over B of JAB SB. Are we all in agreement with this? Now, I'd like to draw your attention on the case odd indeed, where this object, because that, of course, is equivalent to the odd elasticity that you've been hearing a lot about. And what I mean by that is a situation where if I have two spins, for example, JAB is equal to minus JBA. Okay, so let's imagine that this were those two spins. Can you see that if JAB is perfectly antisymmetric, then this thing vanishes? Because SA dot SB is symmetric under exchange of A and B, and this is purely antisymmetric. So an exchange interaction that is antisymmetric, perfectly antisymmetric, or if you prefer, the odd part of any asymmetric interaction will immediately drop out from the energy function, okay, from this quadratic form. However, an equation of motion of this form still allows to discuss about the JAB that is not symmetric. So I could have equation of motion that perfectly allow this occurrence, but those equations of motion would not follow from a variation of an energy. That is exactly the situation that we've been discussing in the context of the odd elasticity. However, if what you want to do is to discuss phase transitions, typically, actually always, you need to take into account nonlinearities. And this fact that in the discussion of odd elasticity, we truncated the equation, the constitutive equation of your medium into a linear relationship with you, prevented us from tackling these issues. What do I mean by that? Typically, when you solve the Ising model, say with symmetric things, what do? You will define an order parameter, say the average magnetization, let's call it phi. And there will be, this is something called Landau theory that probably most of you are familiar. And then you will have an energy functional that is nothing other than what is derived from here. And this energy functional would be either a parabola. Maybe I should have drawn it to a different color. Sorry, I'm confused a bit. Give me a second. Let me redraw it. So you will define a variable, which is the magnetization, which is the average over the spin. And then you will define a potential that is defined as A phi squared plus beta phi fourth, plus potential gradient term, if you want to take into account spatial variation. We'll forget about that for a moment. And then the phase transition, and of course, the phase transition corresponds to a change in the shape of this potential when one of these parameters, alpha in particular, changes sign. And pictorially, this is what I was trying to do before. V of phi, you can have two situations. One, when alpha is greater than 0, that correspond to this object being having a minima at phi equals 0. That corresponds to equal amount of spin up and spin down. Or a situation where there are two minima at two position of plus phi star or minus phi star. These are the two ordered phases with positive and negative magnetization. And this corresponds, the second case corresponds to alpha less than 0. Right? So in this whole picture, the phase transition happens at alpha equals 0. And the signature of the phase transition is a change in the morphology of a potential. Okay? Now, if we want to understand phase transition in many body systems with non-reciprocal interaction, we cannot use an energy landscape picture. And so today I would like to show you how you do it using a couple of examples. Before we move on, please notice that it would not be possible to have this transition between this morphology of this energy landscape if I truncated this to quadratic order. So when we did odd elasticity, effectively what we've done is truncating things to quadratic order. When you do a linear elasticity, what you're effectively doing is truncating things to quadratic order in the energy, hence linear order in the constitutive relationship. Okay? You could go beyond, it's just we didn't do it because we did linear elasticity. So today we're going to tackle examples where the nonlinearities are not thrown away. Okay? So this will be generically dynamical systems, nonlinear, obviously, which have a non-variational structure. The dynamics doesn't come from the minimization of an energy. And to give you a sense, in the same way as in odd elasticity, the effect of that K0, when it was large enough, was to promote the propagation of waves. We spent the whole day yesterday deriving the exact condition. Similarly, you could imagine that exchange interactions that are odd could produce time-dependent phases that are not just the static pictures that you're used to see in the Ising model. And before I go on the blackboard and continue with mathematics for the rest of the lecture, I just want to show you what I think is a fun demonstration with robots. Okay, so and if you want to, this paper done in collaboration with Michel Frouchard, who was a postdoc with my group, is now in ESPCI as a faculty. Rio Anai was a postdoc with my colleague Peter Littlewood, who is now a faculty in the Yukawa Institute for Theoretical Physics in Kyoto, and with Peter and of course myself. So all of the theory that I'm going to describe is in that paper, but also in your lecture notes in a more hopefully friendly manner. I don't know if I'll be able to do all the algebra on the board, but I prepared a handout which is cast in a sort of active learning exercise divided in many steps. You can attempt on your own, but I will also provide the solutions because it's kind of maybe not everybody wants to do it, but you can decide whether you want to do it or not. So what is it that you're going to see on this board? We wanted to do spins that are non-reciprocal, okay? And so what we decided is to say, okay, let's imagine that you have an XY model. An XY model is a variant of the Ising model that I was describing, in which the spins are free to take any orientation in the plane, in the two-dimensional plane. And you have an instance of that up there, right? Now, the only peculiar thing that we're going to do that is different from the, if you like, symmetric case is that we're going to assume that there are two populations of spins, the blue and the red, okay? In the odd elasticity problem, the equivalent of this was two different mode of deformation, say two different shears, so a rotation and a compression, okay? In fact, in the odd elasticity problem, since it has a more complex tensorial structure, we had 4 components, even in 2 dimensions, if you remember. So here, we're just going to say two different types of spin, the blue and red. And the thing that is peculiar is we're going to ask that the blue want to align with the red, but the red want to anti-align with the blue. Okay, so this is essentially the perfectly antisymmetric interaction. And the first question I want to ask is, what happens, right? If we had a symmetric one, we know what happens. They all align in one direction. Which direction? Spontaneously broken symmetry, they just pick it up. All direction in the plane would be equally likely. But if the interaction is the one that I wrote down there, so this is maximum oddness or maximum non-reciprocity, this is what starts happening. I would like to emphasize, these little robots were not coded to process on their own. If you put one of them, it does not rotate. Okay, there's not an internal torque in either of them. The only thing that we have programmed is this non-mutual interaction between the two. And if you want to understand why that thing is happening, I'm going to do a demonstration. Tell you I have an aspirational experimentalist attitude. Has been frustrated for 40 years, for 50 years nearly. So this is the red spin and this is the blue one, okay? So we said that the red spin wants to anti-aligned with the blue. So it takes the first step. The blue, on the other hand, likes the red, takes the other step. Can you see the dance going on? It's entirely caused by the frustration it's caused by the fact that the two components of the system do not have the same goal. And in particular, they do not have goals that are compatible. If the goals were different but compatible, they would find a situation in which they settle. Instead, they quite literally run in circles, trying to find an optimization that doesn't exist. Okay? Sometimes we like to say that there's a selfish energy, in the sense that each species has its own optimization, but they're not compatible. Okay? What comes out is dynamics. Yeah, I mean, there is a Goldstone mode. No, yeah, sure. Here there is rotational symmetry. So there is a Goldstone mode. But the peculiarity of what's happening is that Goldstone mode is, if you like, activated. The system starts rotating in that space and explores all the ground states that would be normally independently chosen. Absolutely, exactly. In that term, we use a prose that we say that there's a restoration of a continuous symmetry that would be otherwise spontaneous, dynamical restoration of a continuous. Now, besides all these fancy words, one thing I want to emphasize is that if you write down an order parameter, which is the orientation of the blue spin or the red spins, the order parameter themselves will rotate at a fixed angle. So the characterization of this state is not a fixed point of an energy, it's a moving, a limit cycle, something irreducibly dynamic. So if we want to understand phase transition, I'll be more tempted to use the word bifurcations, from a disordered state or an aligned state to this guy, we have to understand the transition from a snapshot to a movie. And that is the difficulty. And that's why you can't just do it with the ordinary techniques of understanding a change in the energy landscape. There's one thing I want to say. Notice that these guys rotate, in this case, clockwise, but they could have as well rotated counterclockwise. That is spontaneously broken. Okay? Unlike the other elasticity was done by hand. Questions? Lara. Yeah, so you can start them as you want, but this angle and the speed at which they rotate, for which we will derive formula momentarily, depends on the matrix of interaction. So here there will be an interaction JAA, JBB, JAB, and JBA. The values you choose control everything in the problem in a way that I'm going to describe. Yeah, well, here we've made them interact everybody with everybody. Can also do pairwise. Doesn't change significantly things. And in fact, we'll do a mean field theory where effectively they'll interact with everybody. Say again? Oh, yeah, it's a spontaneous symmetry breaking, meaning if you do the experiment or the demonstration, whatever, 20 times, or with slightly different circuits, it will go off, on average, it'll go halfway clockwise and the other half counterclockwise. A bit like in an easing model, you're equally likely to go spin up or spin. Yeah, absolutely, absolutely. Because the only thing we coded is not, this is not like an electron in a magnetic field that will move in a cyclotron orbit that is always with the same character. No. Okay, so if you like, it's a spontaneous chiral symmetry break. Is this clear? So this is the type of things we want to understand. I'm tempted to show you one more thing. One of the golden example of what people call phase transition in active matter is the called Wicksek model or Turner-2 equation of flocking. Okay, I don't know if anybody has talked about this in this. Somebody has talked. That's good. Then you know what it is, and I don't have to explain too much. So what happens in flocking? In flocking, depending on the noise, you can either have, here it's on the left, a tiny noise or small exchange interaction, a disordered system where the birds move all in their direction, or on the right in red, you'll have all of them moving in one direction. There is no doubt that this is an out of equilibrium phenomena, because if these guys were not moving, there couldn't be long-range order in 2 dimension by Mermin-Wagner. However, I draw your attention to the fact that if I plot the order parameter, which is the velocity field, it's fixed. The birds are moving, but not the order parameter. So in flocking, there isn't a necessity of describing the flocking transition as a transition from something static to a movie in terms of the order parameter. And in fact, the equation of flocking, in some simplified form, are Navier-Stokes equation, which are the same equation with fluid, plus this part added. And this part added is just a variation of an energy of this form that is forcing the transition. What I'm trying to say is that flocking has a variational structure baked in. I doubt that the birds are minimizing something like this, but that's how it is constructed. As a result, there is no issue in flocking in describing with the ordinary techniques that we love. It's what people would call a pitchfork bifurcation. Okay? It's exactly this. And the only thing I want to get you in your mind is, notice, once you break this direction, the birds move, but the order parameter, which is averages fit, is frozen.
So in this, not this example, but the previous one with the spinning robots, at the end, if I was colorblind and I couldn't see red and blue, it would sort of look like a ferromagnet, where like spin up is counterclockwise and spin down is clockwise. Is that?
No, both of them will be rotating clockwise.
Yeah, so they want to be like they all want to rotate in the same direction. So.
Yes, but they all rotate. You see, if you average, I mean, you can look at it again. If you average the direction of all the blues and the direction of all the reds, they are constantly rotating.
Yeah, so like they're all spin up. Like their angular momentum is all out of sync.
Yes.
So
Yes.
is it like icing that everybody wants to have their angular momentum?
Yeah, but the language is a bit complicated because that only says that they're in the plane, whereas all the dynamics is inside the plane. And that is not described by an Ising variable. It's certainly not by an Ising model. To sort of foster the contrast between the normal flocking, let's assume what happened if these birds had non-reciprocal interaction, non-symmetric exchange interaction. Okay, what will start happening is this picture. And it's not that I want to draw your attention to these special birds. I'm not an expert in ornithology. But what I want to tell you is that notice that here, if I draw the velocity field of the species, they rotate because they no longer have just a fixed direction in which they move. So, can you see the difference between this and the previous moving? And of course, you can have all sorts of situations depending on the parameter, which is disorder. The birds move in the same direction. The bird moves opposite direction. Or somewhere in between where there's this chiral phase. Do you see what's happening? Please notice, when they are anti-aligned or aligned, these are static pictures. They're dynamic only when there's a finite angle. There is neither 0 nor pi. Okay? So if you want to understand the transition from this to this, you need to understand the transition from a dynamic to dynamic order parameter. So this is what we will be calling a non-reciprocal phase transition. Flocking by itself at the continuum level does not have this feature for the reason that I explained before. Okay? There is an implicit energy function that is baked in. Okay? So how do we understand this? In order to explain it in detail, I would like to introduce you to a classic problem in dynamical system theory that where we can do all this song and dance. In fact, it captures almost all the mathematics you've seen, both of flocking and the robots, but it's in the context of pattern formation and is fully amenable to analytical treatment. And that's why I considered in detail in the book, and there is also experimental realization that you can read in the paper. So the name of this thing is Swift-Hohenberg model. So what I'm going to be doing is I'm going to do a bit of an introduction to the Swift-Hohenberg model for those who don't know what it is, which I imagine to be many. And then it's a workhorse for the study of pattern formation. And then I'm going to do a non-reciprocal version of the Swift-Hohenberg model, and then I'm going to analyze it mathematically for you. And in particular, the crucial question that we retain from this movie is, what is the criteria for the onset of these dynamical phases? Where do we see this bird start doing the chiral phase as opposed to alignment as a function of the parameter? What replaces the geometric condition on the energy landscape that is no longer valid? Must be something at the level of the dynamical system. What is it? And we will discover that it's an exceptional point, very much like yesterday. But I have to show you how to think about it, okay? So what is this Swift-Hohenberg model? It's essentially a model that describes the onset of a periodic pattern, sort of a crystal in one dimension. But unlike what we've been doing before without elasticity, we assume that the crystal is already there. The phase transition has already happened, and you perturb it. Here we want to understand the crossover from an homogeneous solution to one with a periodic pattern. And this model that has been, that has a wide applicability also experimentally, and you can read a bit more in the notes, is defined by a nonlinear differential equation. We're going to consider a version that it's expressed in terms of a scalar order parameter, function of space and time. And the right-hand side of this equation contains a linear term. It contains a cubic term, and it contains a term which is 1 plus lambda c squared Laplacian operating on U. Now, these two terms you can easily imagine coming from a variation of an energy. What energy would be? The usual one with the quadratic and the quartic term. But it turns out that also this term comes from a variation of an energy. And if I write it down for you, that energy functional, it would be easy also to understand the physics. Yep. Oh, yeah. I'm sorry. No, wait. This is U. This is U cube. Where do you want to put the square? No. Oh, there's one here. Sorry. Yeah, absolutely. Yeah. And this lambda c, the interpretation, this is for now a wavelength that will set the wavelength of the pattern that or the periodicity of the pattern that we want to describe with this equation, or the onset, whose onset we want to describe with this equation. So this equation, this right-hand side, can be expressed as a variation of a potential delta V with respect to delta U, variation with respect to U, the field. And the potential V is equal to dx minus 1/2 squared plus 1/4 U fourth. But the term that is most important is plus 1/2. And all this 1/2, I don't think you need to worry too much, but check out what's coming. Here there is Laplacian. My writing is even worse. Laplacian squared lambda c squared plus 1 operating on U squared. Okay. If you take the variation of this term, you obtain what's up here. Okay. Now, please notice, how do you get this term, which is positive definite, to vanish? If you have a periodic solution, okay, it's almost nicer if I take this down here and I instead put it 1 over lambda c squared, so that it looks like a qc squared. Okay, so if I put something u, which is ei qx, the first term will take 2 derivatives, okay, and will bring down minus q squared. If that minus q squared is equal to qc, this term will vanish. So this term is like an energy penalty for having wave modes, Fourier modes, or periodic solution that are not given by one, that do not have a spatial periodicity of lambda c. Is this clear? And if you wanted, you could put lambda c equal to 1. But I just put it in there like that for emphasis. Okay? So the Swift-Hohenberg model has an apparent manifest variational structure. What we want to do is something non-variational. So we will have to put 2 fields of the 2 different fields that are going to make patterns. Imagine that these were 2 chemicals, 2 proteins, and then we have to couple with each other in an antisymmetric way. But before we do that, maybe it's pedagogical to take a bit of time, minimally at least, to understand how you analyze this. Okay? So first of all, I would like to draw your attention to the fact that, let me erase this for a moment, that if you look at this equation, there is an obvious solution of that equation. Anybody? U equals 0. 0, 0, 0, 0. No, but this is not a bad thing to say. That means that, imagine that this U represented the density of a protein. It means that one solution, it's a landscape where it's 0, it's flat. Okay? But now the question is that where the dynamics want to go? Is that homogeneous U equals 0 state stable? Okay? So what we want to do is a stability analysis. And the answer will depend on the parameters involved, particularly crucially on this R. Okay? So whenever you want to do a linear stability analysis, you say, okay, there is a baseline state. We're going to call it, which in this case is 0, is one of the solution. And then we're going to apply a perturbation, which is small, delta uxt, and we're going to study whether this perturbation is growing or not. Okay? So by literally writing u equal this plus that, you plug it back in, you can now find an equation for the growth or decay of delta u. And this is all determined by an operator L, which in this case, up to order delta u squared, this L is simply given by, you can probably even do it in your head, 1 plus lambda c squared Laplacian squared to the power 2. This is what L is. Okay? You can almost see it by inspection. Okay? Now, what I'm going to do now, Fourier transform, as you were doing yesterday. Okay? And I want to know how each mode grows. Because different modes of different Q could grow at different rates. Why? Because there's Laplacians. Okay? So if I Fourier transform this, I can get an equation for LOQ. Okay, I mean, this is perhaps a bit redundant to write them all, but squared. And then the rate at which my, if you like, delta U or Q grows is given by e to the sigma q of t, where this sigma of q is written right there and is equal to r minus 1 plus 2 lambda c squared q squared minus q fourth lambda c fourth. Okay. And if you study this object and you define a rescale variable LCQ, lambda TQ, you can actually plot it. I'm gonna plot it here. You can plot the rate of growth of the modes sigma or Q tilde, because you see everybody comes paired up like that. You put a Q tilde here. And I don't know if anybody, well, you can guess what it is, right? There's a quadratic and a quartic term. And these curves will typically look, this is -1, this is 1. You can study this function, okay? And when you study this function by taking a derivative, you discover that the two maxima are at Q star 1 and -1, okay? So this is for some value of r less than 0. R is this parameter that was multiplying the linear term in the equation, okay? At this moment, it doesn't have a physical interpretation because I didn't tell you, but it will be the control parameter that controls the instability. How do I know that? Well, because if this looks like this for r less than 0, we can now ask the question, how does it look for a greater r? Well, when r is sufficiently great, it will look like this. I'm sorry, this is still a maximum of 1. Should be the same curve, just, sorry, I did a really bad job. Let me redraw it. Right? The same thing translated up. This is r greater than 0. But you may ask, what is the value where this mountains first hit 0? Because that's where there's going to be, immediately above it, there's going to be growth and then an instability. You see what I'm saying? So how do you do it? Well, you take a derivative with respect to Q of this. You substitute in it Q star 1, and you discover that that quantity, sigma Q equal 1, is actually given by R, just by doing a little bit of algebra. Okay? That means that R equals 0 is the, if you like, I don't know how to call it, the marginal case in which you're just touching the axis with y equals 0. Then above it, you will have all of these modes that are going to grow and explode. So what we learned from this exercise, that as long as r is less than 0, this parameter, the u equals 0 solution is stable. When r becomes greater than 0, there must be another solution. Think about the Ising model and what we were doing before with just story here. Now, with a little bit more work here, where is the number 1? Let me go back to, this is something, number 1 here. With a little bit more work, so this is the annoying thing, isn't it? That once I'm here, if I want 4 to, there must be, I know there's no intelligent way because everything we covered. Is it possible? And then I'll adapt. It took me a moment to ask because I was thinking, am I being stupid or not? Which one should never do, like ask the question always. All right, so I'm gonna write in this, you guys can see hopefully in this window, okay? Let me know if you can't. So the story now is, okay, so this goes unstable, but what happens? Now, with a little bit more work, you can prove you can actually, the way technically you do this, you say, okay, is there a periodic solution? So let me try to write down an expansion in sine and cosines. And let's try to figure out how the amplitude of this cosine or sine depends on the variable r. Okay? And if you do this exercise, you don't have to work very hard to discover that a solution of the form a1 cos x fits perturbatively as long as this a1 is chosen as follows. It's chosen to be square root of 4/3 r. Plus, there are corrections that are order of r3 to the power of 2. A perturbation in that. So this is the leading order solution that gives us the shape of the pattern that will arise once we go above r equals 0. Okay? So now we know that if we are above r equals 0, there is a periodic pattern. And we can do essentially a little plot of the amplitude. Let's call this thing here A, amplitude of the pattern, maybe capital A, amplitude A, as a function of r. Yeah. No. We will calculate perturbatively later. So what we're going to do here is, this is r, so this is r equals 0. So the structure of this problem is what people call a bifurcation between a solution here, which is this amplitude is equal to r equals 0, and then here starts two branches, plus and minus, depending on what you pick up from the square root, that either go up or go down, and they go up like square root of r. Okay, for small deviation from the average. So this is the structure, if you like, of the bifurcation. This is all I want to tell you about the ordinary Swift-Hohenberg model. Now, what we need to, and so I mean, I don't need to convince you that, I mean, I don't need to tell you how this guy looks like. I mean, as a function of x, it's a periodic pattern. Now, what I want to understand is what happens when we make an when we have more than one component. Okay, so let me see. Yeah, I'm gonna go back. I'm a bit tempted. Give me one. Yeah, let me write it down on the new board. Well, actually, I'll do it here. We will write it on a new board, but for now, I want to modify. Go ahead. A stationary solution. Yes, because it's not conserved. To some extent, depend how large the noise is. Yeah. So what we're going to do now is the following thing. We're going to assume that you don't have only one U. Imagine that you don't have only one density, but you have two. One called A and one called B. Okay? So I'm going to go back to the normal Swift-Hohenberg, and if you like, do a non-reciprocal Swift-Hohenberg. So what do we mean by that? Let's assume that there is a chemical component UA and a chemical component UB. All right? So now I'm going to use an index I that runs from 1 to 2, if you like, that denotes either A or B. Agreed? So now this equation needs to be modified to have that index, because it's really two distinct equations. one for UA and one for UB. So all of these terms gonna have an I, gonna have an I, and this one is gonna have an I too, okay? To represent the fact that I can either be A or B. But the crucial change that I wanna do, it's here. Because I wanna introduce a coupling between the A and the B, okay? So I wanna write down there an object, let me find the color one. And here, in this notes, we used this symbol that I don't like in this case because I don't want to necessarily denote. Give me 1 second. I don't want to necessarily denote that it's antisymmetric, perfectly antisymmetric, but there is a coupling. Maybe. All right, you will live with it. I'll tell you what I mean in a moment. No, sorry. This one should be still UI. UI and UI. What this epsilon ij is a matrix. This matrix, I don't want it to be necessarily symmetric, but not antisymmetric either. And that's why I think it's a bad notation. Okay? Can you see what I'm done? So what I'm trying to say is that now we have, and if I do this, if this UI epsilon, if this object, if this matrix, which maybe I should just write it, E11, E12, E21, this one, if this matrix is not symmetric because E12 is different from E21, then the right-hand side here is no longer the variation of a potential for the reason that we've been explored by now ad infinitum. Okay? And so the question that we want to ask is, what happens to the patterns? If these things were decoupled, each of them can have its own oscillatory pattern. But if we couple them with something that has both the symmetric part and an antisymmetric part, what do we see? Okay? This is the same question that we asked for the spins, except that here we can solve it analytically in detail. And then I'll show you how to map the two problems to each other. Now, before doing that, I can resist mentioning a couple of things about symmetries, okay? So first of all, I'm going to soon abandon this, but the normal Swift-Hohenberg model has a symmetry, which is translation, okay? The spins had a rotational symmetry, agreed? But of course, if you have a line and you compactify so that it becomes a circle, the difference is not so big. Moving from left to right or right to left is like breaking clockwise, counterclockwise symmetry. This will play a crucial role in what we're going to be doing. Okay, so let's analyze this problem. How do we analyze it? So here, I'm going to introduce you to an idea, or mention it for those who are already familiar with it, which is known as amplitude equations. It's really I have to say, one of the bread and butter, whatever it is, something you should know. And in my opinion, the study of dynamical system, or if you prefer non-equilibrium pattern formation, and the study of active matter cannot be done independently. Proof of that belief is that in my book, which it's a book whose content I mostly agree with, which is not surprising given that I'm an author, but it doesn't always happen with my own papers. The chapter of active matter, I think, is 9. And the chapter on non-equilibrium pattern formation is 8. And they draw, and this connection is emphasized all the time. I'm going to show it to you here in a moment. So what is this amplitude equation idea? I return there. So I'm going to assume that in general, my solutions, I can erase this. My solutions will have a periodicity like the cosine that we figured out here. a periodicity, say this one here, but on longer time scales, go away. On longer time scales, the amplitude of this periodic solution will have an envelope, okay? An envelope that grows, that I'm gonna call A, X and T, that grows very slow in space and time. It's like an adiabatic treatment of the problem, okay? And what we would like to do is we would like to start from the equation for U and derive equation for this amplitude, okay? And of course, in this case, the periodicity of this pattern is lambda C, the one that is singled out by those. But once we start perturbing it, there could be some dynamical things occurring that changes, but we assume that these changes are gonna be very slow. Now, one thing I want to review for you or emphasize is, let's think of this amplitude as something that has both a real phase, the real part, and a phase, phi, okay? And now the question I want to ask you is, what is the effect of adding a delta phi? So once again, if I have a pattern, and I do this transformation, can you see it that will correspond to translating the pattern? Okay, by an amount delta phi divided by the by the wave vector. Okay, so if I have a pattern that maybe I should go to another blackboard or do it here. If I have a pattern that is like this, if I apply the transformation, the new pattern will be like this. And this is the x-axis. And this shift is going to be delta phi divided by QC, or KC, whatever you want to call it. Okay? So why am I doing all of this song and dance? Is because it's very useful to analyze the system of equation. And as a matter of fact, even the original dynamical system in terms of amplitude equation. So what you have to do now is you have to write down two amplitude equations, okay? One, let me go to the other board. One which is for UA and one for UB. Okay, so UB will have its own amplitude that I'm gonna call, I don't know, 2. And UA is gonna be, you're gonna have its own amplitude, and I'm gonna call A1. Okay? And so there are two ways now to proceed. One, you take the definition of U in terms of the patterns. So there you go. You start here. Can you all see what I'm doing? If I write within this board, these lines, okay. So the definition of U, each U, UI, that could be either one or the other, is UI of X equal AIX EI QCX. Okay? And I can run from 1 to 2, depending on whether you have A or B. Okay? Now, if I take these ansatz and I stick it in the system of equation and I massage them, I'm going to get a set of equations for the A1 and A2. Huh? No, it can have a time dependence, and it will come if it's included in the AI. And in fact, there will be. So I just didn't write it. Okay. Now, what I'm gonna do now is to write down explicitly the answer to the two seto-coupled equation. Okay. Now, if you're a pro at this, you don't even do the algebra or deriving it, because you will be able to see, based on the symmetries that exist in the initial equation, what terms are allowed or what not. But the way that is straightforward, you just substitute, do a bunch of algebra, go for it, and here's what comes out. The first equation is dt, and I mean, you're gonna see some terms are really, maybe any person could have guessed them, right? So dta1, okay, well, that's pretty damn obvious. Then there is another one, but I mean, this is the polynomial one, I cannot treat. But then there's gonna be this one here, okay, that comes from the coupling. So, because you remember there was that matrix here, eh? You remember this story. So this matrix will couple U1 to itself, but also to U2. So the coupling to itself is just called E0 here, and the coupling to A2 is called E12. Okay? And then there's going to be a nonlinear term. And this nonlinear term is what remains of the cubic nonlinearity inherent in that system, which has this form. And there's no gradient terms because we decided to just consider the amplitude at an extreme field level. But then there's going to be also another equation. This equation is going to have the form E0 A2 plus E21 A1 minus G A2 squared A2. Okay. Got it. Say it. Yeah, so remember that A1 itself is a complex quantity. Okay, so the cubic term is written in this way, essentially to preserve the symmetries of this problem. This problem must have translational symmetry and reflection symmetry. And that combination satisfies those requirements. A less direct answer is to say, once the substitution is done, that pops up. But the reason is because of this. Okay, so now what we're going to do here, I'm going to just say, I'm going to assume that E12 is equal to, E21 and E12 are equal to epsilon plus epsilon minus epsilon. So look at this. If this epsilon minus didn't exist, E12 and E21, or epsilon 12 and epsilon 21 would be equal. The system would be perfectly reciprocal. This is not what we're interested in. G is whatever comes out of the nonlinear term, or the prefactor of the nonlinear term, which is inherited in part from here and in part from other places. Okay? Yeah, exactly. They're related to those things. Yeah. And one of the things that you're going to see is that the reason why I'm a touch cavalier is that what I want to show you is the structure of the bifurcation that emerges. And you'll see that it doesn't depend on these G's, etc. Okay? But I mean, in principle, all the numbers that exist here are derived from the parameters that you had in your original model. Once you do that. Okay, so this is our starting point. Now we have to massage it a little bit. And some of the massaging and the previous steps you will be doing in this exercise that I prepared. But let me sketch the crucial things. So what I want to do now, I want to, first of all, for each A1, I want to write it the amplitude times the phase. Okay. Okay. And what I'm going to do is I'm going to try to derive an equation for the difference between the phases and the sum between the two faces. And you see why. They give us very important information about what's going on. And I want to work in a limit that I find particularly interesting for me, which is this. The limit in which non-reciprocity can be strong. You see, look at this, in particular, focus on this last relationship. So this condition, I just give it to myself for simplicity of doing a little bit of the algebra. But I want to have the non-reciprocal part, coupling, the non-symmetric coupling between the two fields, to be large compared to the symmetric one. Okay? Because this is the limit where I'm going to see some effect for sure. Okay? So now we have two options. Either we continue to do the mathematics and we derive the result and then we see what the numerics give, or we look at the movie and then we derive. Which one do you want? Movie first. Yes. It's good because it goes opposite to my instinct. Good, good. Okay. No, but there's a pedagogical sense to it. We will return to that momentarily. So, yep. So, the movie that I want to show you is, now these are two faces. Whenever, not two faces, two patterns. This is the UA and the UB, or U2 and U1. Don't be too fussy about how we call it. In the limit in which the non-reciprocity is large, so this is strongly non-symmetric, what you see is the following. Either moves to the left or it moves to the right, spontaneously broken symmetry, restoring the initial translational symmetry in a dynamical fashion. More crucial, though, the speed at which this guy moves, you can extract all of these things numerically, depends on how much, how non-overlapping they are. If they happen to overlap, they don't move. Remember the birds. When they're aligned, the order parameter are frozen. When they're anti-aligned, also frozen. The chiral thing that was rotating was only when there was an angle in between. Okay? So now, why probably was a good idea to actually use the slide, the movie first, is that if you, except, this analytical stuff is done for when you don't have a computer too. But okay, whatever. Here, notice that there is a separation between these two. That is parameterized in the language of amplitude equation by the difference in the phase. Because as we emphasized over here, there you go. Add the delta phi to the phase of the amplitude. That divided by QC is the spacing between the two. So if you like, this thing here is phi2 minus phi1. Okay? So this is it. This is the movie. It was not particularly long. And now we can continue our march towards the result. So if we take these two ansatz, or these two expression for A1 and A2, again, we substitute here, do a lot of algebra, take advantage of this condition, we can extract equation for two quantities that are crucial. The first quantity is defined as phi2 minus phi1. This tells us about the separation of those two patterns, the degree of which they're not on top of each other. And the other one that I'm going to call phi bar is be phi1. If you like, this is the center of mass, not of mass. A dt, a non-vanishing derivative of this quantity would mean that the patterns are moving. So let's do a little drawing here. Let's do a little drawing. The little drawing is indeed red, blue, yellow, maybe. Okay, let's do it here. There is the blue pattern that you just saw in the movie. There is the red pattern. And there is this distance between the two. It's called delta phi. And then if there is, let me call it delta phi. It's called delta phi. If there is dt phi bar, that's to say that this quantity is non-zero and is a number, 5. That means that these guys are moving, right? This is the speed. Okay. All right. So I'm going to write down the result of plugging this 2 here and doing all the algebra. You will rework it out if you decide to do so in the handout that Eric will post on the school website. The answer is extremely interesting, in my opinion. And let's write it down. Let's revert the natural course of Blackboard here. The equation is really quite, the form is really quite interesting and is the following. dt delta phi is equal to a constant that I call alpha that depends on all those constants that I've introduced in a way that you will calculate in your homework, minus another cubic correction. Now, look at this. This is absolutely unimpressive because this is a pitchfork bifurcation. That is to say, this is dt delta phi, and this is the derivative of something of an energy, essentially, that's quadratic and quartic in delta phi. Can you see that? So this is totally potential. But that's only one piece. There is also one for phi bar. Let's write down the one for phi bar. dt phi bar equal, well, this is even more unimpressive looking. This says that the speed at which the pattern moves depends on their spacing, the thing that we saw already from the numerics. But notice that when I take these two equations together, I can no longer write down that as a gradient of a potential. Because there is a matrix that is coupling it. But before we do that, let's try to see the physics that is behind this. Let's study the behavior of the first equation. Let's try to first understand what is delta phi. So let's try to understand the logic. Alpha, beta, and gamma are functions that you will calculate in excruciating detail, but you can already guess phenomenologically. For example, this one is going to depend on epsilon minus. How do I know? Well, because if epsilon minus is equal to 0, the damn thing would not move. And in fact, it's linear in epsilon minus. Okay, because that is the amount of non-reciprocity, right? Remember all of this song and dance. Okay, so if somebody gives you system, some biological thing or some chemical stuff with these two things, with all the initial coefficient, you translate them in this coefficient, you figure out this alpha, beta, gamma, and then that person will tell you, given my choice of parameter, what is the delta phi and what is phi bar, right? What's the spacing between the two? Spacing, I mean the shift between the two patterns and the speed at which they move. And it will be controlled by these quantities that you know how they depend on microscopic. But what is the scenario? Well, it will depend on alpha, right? Because if alpha is greater than 0, what happens? Anybody? Think of rewriting this as the gradient of a Mexican hat potential. It's not a trick question. I mean, maybe it's easier if I first ask if alpha is less than 0. So, okay, let me just write it down. So in one case, I think that you guys know the answer, it's just that you're confused with which potential. So there are two possibilities. If alpha is less than 0, there's a delta phi equals 0. If alpha is greater than 0, there is a solution that is given by delta phi equal plus minus square root of alpha over beta. In other words, for some choices of this parameter, they will be on top of each other. But if they're on top of each other, the speed will be 0. Now, it turns out that this equation has been derived by Taylor expanding. If you didn't Taylor expand, here there wouldn't be a delta phi. There would be something else. Can anybody guess? Based on the fact that when the patterns are also 100, when they are not only on top of each other, but with maxima coinciding with minima, remember the birds, aligned and anti-aligned, they were still not moving. So when this becomes, with this delta phi is really a Taylor expansion of a sign of delta phi. So both delta phi equals 0 and delta phi equal pi will give you 0 speed. But for simplicity, I Taylor expanded because I wanted to give you kind of a normal form, a simple form of the bifurcation. Yeah. Right. But it depends on the parameters. Huh? Yes, exactly. You have to, if somebody tells you, those alpha and beta depends on those things, right? If somebody tells you this is 1, this is 3, there's a given spacing. If somebody says, well, this is 7, this is 8, this is another spacing. And all I'm saying is that as long as the choice is such that alpha is less than 0, delta phi equals 0, and they don't move. If alpha is greater than 0, there will be a non-zero solution that depends on the actual value of alpha and beta, which is given by here. And once you do your homework, you will know how this depends on epsilon plus, epsilon 0, epsilon minus. And the moment which this is not 0, then you will have a net motion of the two patterns, either to the left or to the right, depending on which of the two solutions you pick, which is spontaneous symmetry break. Okay? So the topology of this problem, if you wrap the line on the circle, is absolutely identical to the problem of the flocking. Okay? And I'm going to show you the numerics to support that. The analysis is much more difficult, although done in that paper. Okay? So I think there was a question, Lara, maybe? Huh? I just did a polynomial thing. I could have, even if I keep a cubic here, it will not capture the periodicity. And that's the kind of crucial thing. And of course, if I don't, sorry, another thing. If I don't put the cubic term here, I don't get the phase transition. So I retain the minimum amount of terms that give you a qualitative idea of what's going on. The part that I miss is that I would have loved to have the sign delta phi here, just because it tells you that there are two solutions that don't move. And you'll see that, you saw that for the birds. Numerical simulation of the full set of equations.
These two amplitude equations.
Yes.
Gradients.
Yes.
And these are just nonlinear Schrodinger equations. Solid.
Right? Not necessarily. Depends on the amplitude. Depends on the regimes. Yeah. Yes. Yes. And also, I mean, we're doing mean field. So when we solved it on the computer, we solved the field equation without the gradient. But even with the gradient, there is a regime where this is true. Yeah. Yes. Yeah. Parity. I mean, the way I like to think about this is the following. I mean, Mermin Wagner, we completely don't care here because doesn't exist. I mean, there's no reason to exist here. But the way I like to think about your point about the symmetry is the following. So in the initial problem, there's translational symmetry or rotational symmetry. Indeed, continuous symmetries. They are spontaneously broken. So you pick up, boom, or one direction. Now you switch on this non-reciprocal term and you restore that continuous symmetry dynamically. Meaning that since now that guy rotates, will span the whole manifold of ground state that before were spontaneously selected. How he spans it, whether clockwise or counterclockwise, is related to the parity symmetry breaking that is associated with that. But there is a restoration of a continuous symmetry. Do you see what I'm saying? Say again? But this is 1D. I just constructed for you to be the sim. Oh yeah, you can do 2D, 3D, whatever you want. But I constructed this for pedagogical reasons, just to show you the nature of the bifurcation. And then we can go back to the birds. Those are two-dimensional. There is still the structure of the bifurcation that is the same. So this bifurcation is not a pitchfork bifurcation, which is the top one in isolation. With the one at the bottom together, it's called a drift instability, in part because of this drift term that exists. Now, notice my comment from before. That this object, that this transition, that this bifurcation is non-potential, is particularly useful to expand this equation around the delta phi equals 0 and an arbitrary phi bar. Let's write down those equations as a matrix. And you will see a very familiar matrix structure appearing. So there's going to be dt that operates on delta phi and on phi bar. And I guess you can even read from here what those coefficients are, because it's a very easy linearization to do. So there's going to be alpha here, gamma here, 0 here, and 0 here. Okay. Notice the question about the symmetry and the translation. None of these guys depends on that. That's the Goldstone mode. Okay. But the aspect I want to really draw your attention, which has been the leitmotif for this thing, is that in the same way as the original fields were asymmetrically coupled, this matrix is also asymmetric. Okay. Well, manifestly, I would say. Okay. So this is again a case that I can write as a potential. So it's a non-potential dynamical system. Simple, but non-potential. Now we are in the position with one more step to ask the question that we wanted before. So if geometry of an energy landscape is not the right way to understand this, what is the criteria, the dynamical criteria we have to seek for the onset of the traveling solution, or the time-dependent many-body phase that is described here? What happens to this matrix as you consider alpha that is progressively decreased all the way to 0? You will, in your homework, study that by putting that thing in Mathematica. But first and foremost, notice that this matrix is not guaranteed to have orthogonal eigenvectors. Anybody? Why? Because it's not symmetric. Same song and dance as we were consideration that we discussed for when we wanted to say the onset of the active waves. But what happens when alpha goes to 0 is particularly peculiar. Matrix of this with this form have a name. For people who remember linear algebra, Jordan form, indeed. And there's something a little bit funny about them, which is, anybody? First of all, I mean, you can see from inspection that even when this alpha is equal to non-zero, there's a zero eigenvalue here, which physically corresponds to the translational symmetry of the model and the fact that these are all zero. So that's the Goldstone mode. But then there will be also another eigenvalue that is non-zero. And in your homework, you will literally track it as a function of alpha. As alpha goes down to zero, this other eigenmode or eigenvalue goes to zero too. So when this is zero, you have both eigenvalues are zero. The eigenvector become coalescent. They coalesce, meaning okay? And so this is what we call an exceptional point. So besides this example, what you will do when you face a similar situation in another problem is take the equation of motion, with some technique of your choice, try to find the Jacobian of the transformation that describes this evolution. In this case, in the most simplified description is this matrix. Please notice this is entirely a dynamical characterization, and look for exceptional points. They will mark the onset of the time-dependent phase. Let me summarize with some drawings. So the first drawing, actually, you can, once you know how, which you calculate at home, how alpha, beta, and gamma depend on the parameters epsilon 0, epsilon minus, and epsilon plus, you can do by hand, drawing by hand, a phase diagram of whether you're going to have static phases or the chiral phase, which is where the two patterns are moving. And so this phase diagram will look like this: E minus divided by E naught, and here there will be E plus divided by E naught. So what is that? This is a bit like the ratio of the odd modulus to the shear modulus. And this is, sorry, the ratio of the odd modulus to the bulk modulus, and this is a bit like the ratio of the shear modulus to the bulk modulus. Why? Because E plus is the symmetric piece of the coupling. E minus is the antisymmetric one, is the non-reciprocal. So I can already say that if I'm on this line where the non-reciprocity is zero, then I know what happens, right? Imagine that I can either have aligned or anti-aligned, because it will not move, okay? The birds can either all go one way or opposite ways. There cannot be a dynamic phase. That's on this line. So on this line, if I have to color anti-aligned or anti, and please notice when I say anti-aligned, it can mean either the arrows of the birds or the spins, or if I'm talking about the patterns, aligned means delta phi equals 0, anti-aligned delta phi equals pi. It's probably not the perfect term, but whatever, you know? So this is anti-aligned, this is aligned. You see, ferromagnet, antiferromagnet. But if I am at a finite value of non-reciprocity, I know that I can have the time-dependent phase, right? In particular, when epsilon minus is large, that's what we calculated, right? But how large does it have to be? Well, that will depend on alpha and beta, right? And since alpha and beta depend on these quantities, once you know that dependence, you are able to draw the following by hand cartoon that will tell you here is red, here is blue. So here is anti-aligned, that's to say delta phi equal pi. Here is aligned, that's to say delta phi equals 0, okay? And in these other portions that maybe in an excess of chromatic zeal, I'm gonna also do in yellow, here leaves the chiral phase. And by chiral, I'm calling both the one that go clockwise or counterclockwise, or the one that go left or right. And this separatrix that separates the time-dependent to the time-independent. Imagine that I'm marching For a finite value of non-reciprocity, I'm tweaking the reciprocal coupling. I'm marching from the anti-aligned phase, which is static. I hit this line, I become time dependent. What is this line? What that line is, would have been lovely to have another color, but that's it, there's none. So it's the exceptional, it's a line of exceptional points. Very much like the line that we drew in the phase diagram that we derived for the active waves of the outer elasticity. Okay? Now, can you see what I've done here? I've drawn a finite, it's a one-dimensional cut to the phase diagram. Here nothing moves, doesn't move again. I wouldn't use that language. I would say that this is an exceptional point mediated phase transition. So at this level, you cannot see it because it's mean field. So I can't answer that question at this level. What we've studied in the easing model, for example, is that there is accompanied by divergence length. I want to show you one more thing. And I'm sorry if I take maybe another 2 minutes. Is it possible to switch back the... This is a, I want to show you numerically, 1 second, the same, so you realize this has been calculated from this equation. I want to show you what happens if you try to make this same plot for the Vixak model, okay? Is it gonna? I think it works, no? Yeah. So what is this showing? So first of all, this thing here, up here, is the phase diagram for the Vixak model. Notice that in the Vixak model, you can do a sum of the JAB plus JBA and the difference. If they were equal, the difference would be 0. That's equivalent to the epsilon minus. Whereas JAB plus JBA is the epsilon plus. Okay? And notice that you have the anti-aligned and the aligned, and you have the, in whatever, pink, you have the chiral phase. What this plot is, for the same model, is calculated, this is the answer to your question, the speed at which they rotate. I have an animation, but it's not particularly good because the speeds are not varied, but it's still better than nothing. You see, when the birds are anti-aligned or aligned, the order parameters are static. You remember the picture we started. So the speed of rotation, omega SS, this is what we called in the pattern dt phi bar. Okay? That goes from 0, and then it starts growing. Okay? And then it goes to 0 again when it's anti-aligned. But what these movies don't capture is that this speed should really be shown to increase as the angle changes. And how does it increase? Precisely according to this type of equation. Okay? And the last thing that this is showing here is even in this system that is a bit more difficult because there are 2 vectors in the plane. So the dimensionality of the space is 4. V1x, V1y, V2x, V2y. Still, there is a Goldstone mode, 1 eigenvalue, that is always 0. That corresponds to this. And then there is a second eigenvalue. It's going to 0 at the exceptional point. That's exactly what happens in the system when alpha goes to 0. So if you like, these one-dimensional things are cuts of that 2-dimensional diagram that are precisely what we calculated analytically here at the level of the topology of the phase diagram. The 2 problems are somewhat different. So again, the lesson to be learned, this phase transition are mediated typically by the onset, by the presence of exceptional points. And there is a lot of interesting effects that also arise when you put noise in here, including amplification of noise. But I don't really have time to talk about it. The only thing I would like to do is this drawing that I like. So normally, when you think about phase transition, there's this Mexican hat, okay? And so there's what people would call a Goldstone mode, which is moving at the bottom of the sombrero hat, maybe, yeah? And then there is something that some people would call a massive mode, which means moving uphill. Right? These are the two eigenvectors that at the exceptional point coalesce. So at the exceptional point, what is happening geometrically is that those two eigenvectors that we calculated, the red and the yellow, boom, they coalesce onto each other. So that means that a way of thinking about these systems is the reciprocal part of the energy that will exist if you have symmetric coupling can make a potential. But the dynamics is not merely a descent down that potential. There is a component that is not downhill, but isohill. That is the one that cannot be captured by an energy. And of course, when you go to the exceptional point, the projection is entirely in that manifold of the Goldstone mode. And that's why the noise is amplified. Because no matter how you disturb the system, it sends the response in the easy direction. Okay? Now, with that, let me just tell you that these things are not entirely crazy. There's even experiments. And some of these experiments we discovered, there's even manifestation going down 20 or 30 years ago. If you look at them carefully and you revisit them. My absolute favorite is this one. I don't know, this must be a bias, a geographic bias from where I was born. Imagine that you are in summer heat here in Boulder 2, and there's an overflowing fountain, which in retrospect is a bit wasteful. So the water flows in the radial direction. What can be observed is at the rim, a pattern like this or this that moves either clockwise or counterclockwise. If you write down the amplitude equation for this type of systems, you will find an exceptional point mediated bifurcation. And it's pretty much the same mathematics that is governing the things that I've showed you. So bottom line is, transitioning system with non-symmetric interactions from static to time-dependent phases are mediated by exceptional points. And that's how you figured out some of their characteristics. With that, let me stop. Thank you very much for your attention. Question. No, you can have a point. I mean, in fact, I mean, you can, I mean, naively, of course, in one dimension, you have a point. In our system is never in the system that does not break that does not break spontaneous symmetry explicitly. That breaks symmetry spontaneously and not explicitly. There's always a manifold that is aligned. Yeah. But I don't see a reason why there couldn't be another point in the case in which the symmetry is explicitly broken. Any other question? Here is not entirely obvious at the level of the field equation, but once you take this nonlinear equation, there are two dominant modes. One which is a cos of x, and the other one is a cos 2x, for example. You see two dominant periodicities. And when you write down the amplitude equation, these two periodicities are coupled in non-symmetric ways, and that triggers it. So it's not quite a realization of fields that are non-reciprocally coupled, but at the level of the amplitude equation is almost identical. Okay, so maybe I misspoke in saying that it's been around for a while, but it's very similar to the mathematics at the level of the. And of course, it can happen because it's a driven system. These are the system like liquid crystal solidification fronts. So there's a temperature in gradients. These things are moving. So they're all driven systems. Never happens in equilibrium system. Any other questions? Yeah. Yeah. Well, so one thing that we do know, is that we've been able to switch universality class. So, for example, you can have a model that is easing, say, an easing model with non-reciprocity, that you switch on a large non-reciprocity, and the critical exponent go from being the one of the easing universality class to XY. So this we know can happen. I don't know exactly what novel universality class would mean. I would argue that the transition from a swap, from time-dependent phases, those are novel mechanism at the very least. I'm hesitant to answer novel universality class because I don't know if they fit in the old classification in the first place. Well, I mean, the correction to easing, the fact that the fixed point of easing goes into XY, that's certainly coming from those terms. Absolutely. Because it's the non-reciprocal one that caused. Any other question? The XY model, sorry, the Vixek model or the Toner 2, we did do it in 2 dimensions. The Swift-Hohenberg, we haven't looked at it in 2 dimensions. Or if we have, I don't remember the details. In part because we looked at it more like the sort of simplest thing we could do, and in 1D where we can do all the song and dance at this level, you wrote it down. But maybe it's an interesting thing to do. I could imagine it could be interesting because there can be like, how do you call it, non-compatible patterns, and yeah.
I don't remember. Did you get swapped in the 1D Swift-Hohenberg or just chiral?
Oh no, we do have the whole charade of the phases. So what he's talking about is maybe I have maybe a picture is easier. Do I have a picture? So this chiral phase that I showed is not the only time-dependent phase that you can observe. I apologize, I don't have like if you imagine that you have this bird system, you can have a dynamical phase in which instead of rotating like that, they flip. The red becomes the blue, and the blue becomes the red. And there is an equivalent state also in this one here. There's also an equivalent one of the chiral swap. So essentially, all the phases that exist in the flocking exist in this toy model, and they have names because they have to do with the synchronization of the pattern. And there's a table in that Nature paper that I cited where there is a dictionary of conversion of the names in all these various models.
Which section of points do you know about the topology of the graph? Like, can I look at these curves and say, it's a circle?
Not that I can see. Not that I can see. I mean, they depend on it, but I don't know if you can make the inference. Oh, yeah. Yeah.
Could have done Cross-Hohenberg, and then there are all these other way from propagation and all that. To get that also with the check model.
Yeah, I mean, not all of these models will map onto each other, right? I mean, in order to, have the same topology of the phase space, so the phases, they have to be close cousin. But what you could do quite conceivably is pick up your favorite model from the book that you studied in Swift-Hohenberg, or from the chapter of my own book, and that is potential. And yeah, write 2 copies of the field, couple them asymmetrically, and unless a miracle happens, there's a range of parameters where this will happen. And at least a transition from a static phase to a dynamic one. That you will, and you may see actually other phases that we haven't seen in this. Why not? Because after all, I mean, the phases that we see here are the chiral that restores the rotational symmetry, what they call the swap that restores Z2 symmetry, and a mixture of the two. But the fact that we have only these 3 is because we started for something that had only rotation in the plane. If you start with an order parameter, which is some fancy group, then there's more room for dynamic. But maybe the unifying aspect there, I would think, is that there will be generically some Goldstone mode that are some axes that in the original model without non-reciprocity would be spontaneous. You would choose your graph state by spontaneous symmetry. And then the new dynamical phase will just travel in that, along that Goldstone.
Front propagation would look like in this context. So you can have non-linear wavefront propagation. You can also have a transition to chaos, right? Which of course.
Oh yeah. So yes. In fact, I mean, I was a little bit, maybe merciful so notice that the analysis that I showed here is mean field on this board. But you can ask, what if we restore the spatial term? Could it be that actually some of the things that you're calling phases become unstable once you go beyond mean field? You see, there are 2 things you can do. Restore the gradient term, then put noise in it. And you have to test this prediction against each of these perturbations you do. Each of these things can destroy some of these phases, and they do in many cases. One example I want to give you is that actually, if you consider the same model of Vixek with non-reciprocity, and you linearize essentially the operator, including things that have gradients, then along the exceptional lines, generically, you will find the spatiotemporal chaos, a window of spatiotemporal chaos. We can even prove that. So yes, these things can happen, but there are cases where even with spatial structure, even with noise, there are time-dependent states that are stabilized. Example is the Ising model, non-reciprocal Ising model in 3 dimensions. There we proved that there is a stable time-dependent phase. But the fate of these phases, you have to study. And what I showed on that blackboard is only a mean field analysis. Is this good? Thank you.